Hey, this is Horner. We're going to look at number 1 from chapter 2. So these are going to be your chapter 2 solutions. We have a person standing on a bathroom scale. So here is the person standing on the bathroom scale. We're going to make this all from the side view, so it's a little bit easier to see. That's the scale. Here's our person. They're really happy to be on the scale. And they want to know which of the following is not a force exerted on the scale. The first one they talk about is the contact force due to the floor. So I'll actually draw the floor here also. And there is, for the scale, a force from the floor. So here's our scale. We're just going to put S for scale. There is a force on the scale get pushed up, so that is the force of the floor, and then there is a force pushing down on the floor, and that would be the force of the scale. So that one is fine. That's a contact force. A contact force due to the person's feet. So if we think about the scale again, we have the feet pushing down, so this would be the force of the foot, and then we have the force of the scale pushing back up on that person. So that one's fine. We're going to skip this one, and we're going to say the weight of the scale. Now we have the scale itself, and pulling down on that scale would be the force due to gravity, and that is from the Earth. So I'm going to put E here. That is the force of gravity pulling it down, and so the scale itself is also pulling up on the Earth. So this is the force of the scale on the Earth. It's not very big, of course, because the scale is so small compared to the Earth, but it is equal and opposite. The last thing that we look at here, it says which of the following is not a force exerted on the scale. It would be the weight of the person. This person, they are standing on it, so we do know that there's a contact force of the person's feet, but the weight of the person is the interaction between the person, so I'm going to put P for person, between the Earth, so this is the force of gravity due to the Earth, and then the person would be pulling the Earth up, so this is the force of the person pulling up on the Earth. Of course, we're on a very large object, so the pull down can only be equal as much as the person can pull up on the Earth, but that keeps that person on the Earth. These are all third law interactions, which means that they have to be acting on the same thing. And that is the reason why number 1 is the weight of the person, because the weight of the person doesn't have anything to do with the scale. We could get rid of the scale and the weight of the person would still be there. Let's go ahead and take a look at the next problem. This one is number 5. It says an astronaut weighs 175 pounds. They want to know what is that person's weight in newtons. We're going to start with 175 pounds. We're going to use some dimensional analysis to help us here. That'd be over 1. I know I need pounds on the bottom to get rid of the 2 pounds, and then get rid of the pound units here. And then on the top, I need newtons. You would have to look on your conversion sheet to find out that for 1 newton, there are 0.2248 pounds. At this point, we're going to draw a double line to indicate that we're ready to solve. We're going to get rid of the pounds. We're left with newtons on the top. And if you take 178 divided by 0.2248, you'll find out that that is 0.778 newtons. So 175 pounds, it's a typical man, I think, is usually somewhere around 778 newtons or so. That is number 5. Let's go ahead and take a look at the next one, which is number 8. It says, these deal with vectors. In the drawing, what is the vector sum of forces A plus B plus C if each grid square is 2 newtons on a side? So we can go back to what we did in class, and we're going to use the, not parallelogram, but the polygon method to solve this one. So we'll start by drawing the A vector. So there is our A vector itself. Then we're going to go through and draw the B vector. So here is our B vector. Remember, we want to go head to tail. So we started here, drew our first line. Now we're going head to tail with the second line. And then finally we need to do head to tail with the third line. And so there's our C. So this would be letter C. Now we can connect from the tail of the first one back over to the head of the last one. And when you do that, you get this red arrow. And you'll notice that the red arrow fits along just one side of the square, and we know that the grid squares are 2 newtons on a side, so therefore the force for this one um, would be 2 newtons, and it's going directly to the right, and we see that right is east, so it would be 2 newtons east. So here we have our magnitude, and we have our direction. And that makes that problem a lot easier if you use that method. Number 14 uses the same thing. It says rank vectors A, B, and C in problem 8 in order of increasing x component if the x-axis points east. So we can go ahead and draw the x component for each one of these. It's pretty easy to do. So for letter A, this would be our x component. It goes from the tip of the arrow to where the head of the arrow would be, but you can only go in a straight line left to right. For the next one, this one does not have any x component, just kind of sitting there. And then finally for C, our x component would just be going to the left. So this one is negative 2. This one is positive 1, 2, 3. And letter B would be 0. And so if we want to rank these, it would be pretty easy to do. We could just say that this would be C in the x is the smallest value because it's negative 2, followed by bx because it's 0, and then finally we have ax because it is positive 3. So negative 2, 0, and positive 3. And that's number 14. For the next one, which is number 19 in problem 8, wants us now to use the component method to find the vector sum of A plus B plus C, and we know that each grid is 2 newtons on a side. So let's go ahead and let's just break these up into x and y. So it's a little simpler with these because we don't have to worry about the angles because we do have boxes to tell us how long these are. So this is 3 newtons. I'm sorry, this is 3 units times 2 newtons on a side. This would be 6 newtons for A and the x. For A and the y, A and the y, notice we have 1, 2, 3, 4, so that would be 4 times 2, which would give us 8 newtons. For B, we don't have anything in the x, so that would be 0, and then B and the y, notice it's pointing down, so we've got 1, 2, 3, 4, so that'd be negative 4 times 2 newtons for each box would give us negative 8 newtons. And then finally for letter C, we have C in the x is equal to negative 4 because it's 2 boxes. Each box is worth 2, and it's going left, so it's negative 4. And then C in the y is equal to 0. Now we need to add everything up, so let's add up the sum of the x values. That would be 6 for A plus negative 8 for, 6 for A. Our next one, which would be B, is 0. And then finally for C in the x, we have plus negative 4. So when you're done adding everything up in the x direction, this would be 2 newtons. And then the sum of the forces in the y direction here, for A and the y, we've got positive 8 plus B in the y, which would be negative 8. And then finally we have C in the y, which is 0, so we can leave that one off. And 8 minus 8 is also 0, so this one would be 0 newtons. Because we want to find out what is the overall sum, we're going to say our resulting vector squared is equal to the sum of the x's squared plus the sum of the y's squared. But what's really nice here is we don't have anything in the x in the y direction, so we can just do our x's. And so we've got r squared is equal to 2 squared. So that would be r squared is equal to 4. And so our resulting vector would be 2 units, or 2 newtons, to the east. And that is the end of number 19. Let's go ahead and take a look at the next one. This one's number 31. It says forces of magnitudes 2,000 and 3,000 newtons act on 5 objects. The directions and forces are shown in the sketches. They want us to rank the objects according to the magnitude of the net force from smallest to largest, and then explain our reasoning. So for the very first one here, we've got 3,000 going in this direction, and we've got 2,000 going up. Here we've got 2,000, and we've got 3,000. We've got 2,000 going left, 3,000 going right. Here we've got both 3,000 going right and 2,000 going left. Then we've got 3,000 going down and to the left, and to the right we've got 2,000. So let's do the easy ones. One of the easier ones is letter C. Notice that this one's going left, so it's really negative 2,000 plus 3,000 would give us a positive 1,000, and that's pointing to the right. This one is 3,000 plus 2,000, so this one would be 5,000 units pointing to the right, so that one's positive. So we're going to circle the sum for that one and for this one. For these two, you'll notice that they form a triangle, and what we can do is we can think about that triangle would have a side here, but the sum of the two vectors actually points out this way. We know that from that parallelogram method that we did on the first night of class. So this would actually be the resultant of the two. So to find that r, we could use the Pythagorean theorem, and if you use the Pythagorean theorem, we end up with about 3,600 newtons for letter A. For letter B also works the same way, and so this one's also 3,600 newtons. So we've got a couple of these. This one's 1,000 newtons. This one's positive 500 newtons. For our very last one, well, we've got an angle here, and we've got to kind of guess what that angle is. And so what we'll do is we'll draw a dotted line here, and we'll say that that angle is probably about 60 degrees. So we need to find out what is the x and y component of these two. If we do that, we could say that e and the x is equal to 3,000 times the cosine of 60 degrees, and that would give us 1,500 newtons, so that'd be in the x direction, and then letter E in the y direction would then be 3,000 newtons times the sine of 60 degrees, and that would give me 2,600 newtons. So at this point, notice that we've got the sum of the x and the y for this side. We still have an x on this side. So if this one is going 1,500 newtons and we'll say that it's going left, I need to add it to the 2,000 newtons going right. So that would be 2,000 newtons going right, which would be positive, plus negative 1,500 newtons, and this is all in the x direction for E. So that one gives us 500 newtons as a total. So that would be the sum of this guy right here, which we said was about 1,500 newtons, plus this one, which is 2,000, but remember this one's left, and so it's negative. So the overall for letter E, the overall sum of those two in the x direction would be about 500 newtons. So we're going to draw a new one here, 500 newtons. We also have a vector pointing down. We said that that one would be the E and the Y, so that one's about 2,600 newtons. And now I want to add the two, so I'm going to use my Pythagorean theorem. If you use a Pythagorean theorem, you'll get this final vector pointing out down to the right, and that one is about 2,650 newtons, and that is the final answer for it. So to rank these, we would see that from smallest to largest, we would have letter C, then we would have letter E, and then we would have letter A, and that one, remember, is equal to letter B, and then finally we have letter D, and so that one is number 31. Let's go ahead and switch to the next one. This is number 34, so now we're looking at just doing some really basic things. We're going to draw a free body diagram for a car that is driving straight on a straight level road, and the key word here is at constant speed. We also know that the road is level, so we're going to draw a level road, and we'd have our car on that level road. It's a really bad car, I realize that, but we're just going to use a dot because we're going to do a free body diagram. And we know that pointing straight down would be the force due to gravity on that car. Pointing straight up, we talked about this force. This one's called the normal force. so that is Fn. Pointing to the right here would have to be the force of the engine. So it'd be kind of like that thrust force we talked about in class. And then pointing backwards would be the force of friction of the tires on the road. So that would be all of the forces that are acting on that car, and that's number 34. For number 35, this one's a little bit different. We have a sailboat. It is tied to a mooring line, and that sailboat weighs 820 newtons. The mooring line pulls horizontally towards the west, okay, on the sailboat with a force of 110. The sailors are stowed away, and the wind blows from the west. The boat is moored on a still lake, so no water currents push it. Draw a free body diagram of this thing. So right now we know that we have our boat. Pointing straight down would be the weight of the boat, which is the force due to gravity. And so this one is equal to 820 newtons. We also have a force of the water. We call this the buoyant force, so we talked about it in class. It is equal to 820 newtons also. These are equal and opposite because the boat is sitting still on the water. It's not bobbing up and down. It's not sinking, and it's not all of a sudden rising up out of the water. We have a mooring line which is pulling on that sailboat, and it's pulling on the sailboat with a force of 110 newtons. So this would be the force of the mooring line. And the wind is blowing from the west, so we know that the wind is blowing this direction. It's blowing towards the east. It's going from west to east. So this is the wind direction. So we would also have a force of the wind. And because this boat is sitting still, we know that the force of the wind, so we'll say Fw here, is equal to 110 newtons. And that is number 35. For the next one, we have number 39. We have a truck driving on a level highway, and it's acting on by the following forces. So we have a downward force of 52 kilonewtons, or 52,000 newtons. We have an upward contact force of 52,000, another constant force due to the road of 7,000 newtons, and a drag force due to the air of 5,000. They want to know what is the net force acting on the truck. So let's go ahead and draw a dot for our truck. We know that its weight, so its force due to gravity here, is equal to 52,000 newtons, or 52 kilonewtons. We have an equal and opposite force of the road, and that would be the force normal, and it's equal to also 52,000 newtons. So all of the forces in the y direction are zero, which is good. We have a force of air resistance, so we're going to put 4F air here, and they said that this force is about 5 kilonewtons, 5,000 newtons. And then we have another contact force due to the road, another contact force on the road, which is probably the engine pulling on that car, and so that force is pointing to the right. So we're going to just put FC for that contact force, and they told us it is 7,000 newtons, or 7 kilonewtons. These two forces are not balanced, so we're going to need to add the two together, so that'd be 7 kilonewtons plus, and then our air force is negative 5 kilonewtons. And so the sum of the forces here in the x direction are going to be equal to 2 kilonewtons. And we say that that is east. And that is the end of number 39. I'm going to go ahead and stop here, and I will put another video on for the rest of the problems for this chapter.